Thank you very much. It's really cool to be here. This has been a great program. The conference was awesome. I'm having a great time. And it's always great to be here with the defect crowd. Today I'm going to tell you about a paper I wrote earlier this year with Theo Jacobson and Kostas Rampadakis. And really, the idea of this investigation was to try to tackle the sort of, open problem. Is how do you think about confinement in 3+1D gauge theories without one-form global symmetries? Right. So you might even just stop me just from writing this, because sort of the modern viewpoint is that confinement is sort of defined when you have a one-form global symmetry, which is preserved. Or rather, you would say that if you have a gauge theory with a one-form global symmetry, the confining phase is a one-form preserving phase of the theory. And this is nice because there's once you have a one-form symmetry, you have an order parameter. So in gauge theories, with say just pure gauge theories, you have the Wilson lines as some sort of order parameter. And here, so I'm thinking about the one-form symmetry as the center symmetry of the gauge theory. Yes, yeah, this is the center. Yeah, good. So gauge theories often have a one-form symmetry, but I only want to talk about center symmetry here. Yeah, so the center symmetry preserves the Wilson lines, and then you can sort of distinguish the different phases by what the expectation value looks like in the infrared. That is in the sort of limit as the sort of radius of the curve goes to infinity. We know that if the Wilson line approaches 0 exponentially fast, so I guess we typically say that this falls off like the area of the curve, and the other one is some sort of perimeter. But in sort of the modern language, you would actually say that in this R infinity goes, the radius of this curve goes to infinity. This goes to 0, and the perimeter log goes to 1. And the reason is that if you have a perimeter scaling of your curve, you can actually add a gravitational counter term, which cancels this perimeter scaling. So in a sense, this will the leading order term here is 1, and there is sort of no counter term you can add, local counter term you can add to the Wilson line, so that to sort of get rid of this area fall off. And so in this case, we say that the Wilson lines are trivial, and the theory is confining because there's no line operator that's charged under the one-form symmetry that has a non-zero expectation value. So this is also G1 preserving. Whereas when the expectation value goes to 1, we say that there's a charged operator with an expectation value. So we have one-form spontaneous symmetry breaking, which is some sort of topological order, which we also call as deconfinement. And what's really nice about this sort of way of thinking about confinement is that since we know this is a global symmetry, there's actually a phase, we know that there has to be a phase transition going from this phase to this phase. And that's perhaps clear by the fact that this one has topological order, whereas this can be matched by a trivially gapped phase. Okay. So hopefully this is somewhat review. But the reason why we might be interested in confinement in the three-dimensional or four-dimensional theories without one-form global symmetries is that this is what happens in the real world. So for example, in the standard model, there is no, well, we think that there's no one-form center symmetry to diagnose confinement. Maybe I'll say in QCP. Yet we still know that in the real world, the infrared theory is gapped, except for the photon. But we know that essentially the color, the SU3 gauge field confines. So there is some sort of notion of confinement. And so the question maybe we want to ask is there a better or maybe different notion of confinement that sort of also applies to the real world? Cool. So one thing we know about one-form global symmetries is that when you turn on a background gauge field for the one-form global symmetry, what this does is it turns on some sort of discrete flux in the gauge group. So here I'm considering some sort of gauge group G, and I also want to take the center of the gauge group to be some Zn. I'll just take this as simplification, although everything sort of generalizes for more general centers. Right. So we know then in this sort of scenario that when you turn on a discrete flux, what you're actually doing is you're going from some G gauge theory and you're restricting to some G mod Zn gauge field with a fixed obstruction class, I guess I'm going to call it B2, which is cohomologically classified by this BG mod Zn with some values in Zn. So this is what we mean by turning on some discrete flux. So this is nice. But what's cool about this is that we know that this behavior is actually a little bit more generic. This is not a requirement of having a one-form gauge field. In fact, this happens also when you have, so if you have a gauge field plus some matter, where the matter transforms faithfully under some Lie group. I'm going to call this curly G, which is the case when you have some flavor symmetry that acts on the matter, and there is some discrete identification between the gauge group and the flavor symmetry group. So in this setup, you would say that the zero-form global symmetry is the one that acts faithfully on all local gauge-invariant local operators. And so essentially what's happening is you're saying that there's an identification of part of the flavor symmetry group with the gauge group, so that only the only gauge-invariant local operators are the ones that are transform under this quotient. So example we maybe want to have in mind for this whole talk is an SUN gauge theory plus n complex scalar fields in the fundamental representation. So in this case, you'd say that the scalar fields, essentially the center of the gauge group will be identified with the center of an SUN global symmetry that permutes all of the scalar fields. And so essentially the scalar fields transform under this. I'm throwing away the U1 part. So that the flavor symmetry is a PSUN global symmetry. And so if I couple to GF bundle, generically there will be some W2 obstruction class which reminds you that this is a PSUN and not an SUN. And then when you couple to bundles of this type, this also turns on a discrete flux in the gauge field, which is identified with this mod n. Cool. So this is maybe a nice observation, but something important about this is that in these sorts of theories, because of this identification, there is no center symmetry. Or, well, I'm going to take the case where there's no center symmetry. So I'm going to restrict to this case and saying the entire center is identified with parts of the flavor symmetry group. And this implies that Wilson lines are not protected. In other words, they are endable. Yeah, okay, good. Yeah, so essentially what you do here is you say, actually what this means is that so B2, yeah, when you turn on W2, you're turning on, you're restricting your SUN gauge bundle actually to a PSUN gauge bundle. Yeah. And then B2 is sort of classifying this obstruction. So essentially this is like a discrete flux that you're just turning on in the gauge bundle, which you might not have thought you were able to do because you don't have a one-form symmetry. Yeah, it's not a B2, it's more like a W2. I just wanted to.
Maybe fluxes of the gauge field are related to W2 or whatever?
Yeah, that's right.
Okay.
Yeah. Yeah, so this is like the W2 of the gauge group if you want. So it's a fixed class. You're not summing over it or anything. Okay. So the question actually we were originally trying to answer is, well, this is a nice observation, but does this tell us anything? Can you use this to do any physics, even though you don't have the power of a one-form global symmetry? And it turns out the answer is you can do a lot of cool stuff with it. So I want to now take a step back and introduce this notion called symmetry fractionalization. So symmetry fractionalization is a phenomenon that happens if you have a theory with line operators and you have some zero-form global symmetry. And the symmetry fractionalization occurs when the zero-form symmetry acts projectively on these line operators. So given a line operator, L, you can associate some cohomology class, which is in BG0, U1. And what this is classifying is the action of essentially junctions on the line operator. So here's my line operator L, and here I have some junction. So I have G, H, B, H. And since these operators are topological, what I can do is I can sort of move this junction past the line. And what you get is that the line operator is multiplied by this phase omega L of G comma H. Okay. So whenever you have a phenomenon like this, you have to ask a little bit about the counter terms. And so it's important that this is a cohomology class. So that means that essentially any sort of local counter terms that you can dress these intersections by will be some one cycle, and so it will not affect this second cohomology class. But something interesting to note is that yeah, that's right. Yeah. Yeah, that's right. Yeah, but so a consequence of this is that up to counter terms, if essentially, if G0 is abelian, then this cohomology class vanishes. So a priori, or I guess naively, it looks like you cannot have some sort of symmetry fractionalization for abelian global symmetries unless you're being a little bit, unless you have some other physical insight. So for example, if these line operators have some fusion rule like L to the n, so here I'm imagining there's one direction this way, and then d minus 2 directions coming out of the board. So, yeah, so these are d minus 1 dimensional surfaces. And so this is a d minus 2 surface, and that can link with the one-dimensional line operator. Yes, that's right. Yes, sorry.
What did you say? H2, G0? C2 times C2 is...
Yes, sorry. Yes, continuous. Are you sure that's not for z coefficients? That's for U1. Okay, then yes. Thank you. Yeah. But there are many nice examples where you might want symmetry fractionalization for a U1. Like, for example, if you have, like, I think if you have one flavor QCD, this can happen. So, yeah. There's a lot of papers that are written about this case, where they realize you can sort of have these discrete fluxes, and then go ahead and sort of do the whole story I'm about to tell you with it. But we're a little confused about this case, if there's actually some physical content to it or not. Okay. So there's sort of two different cases for when you have symmetry fractionalization. The two cases are essentially, one is when there's sort of no one-form global symmetry, which is sort of more generic, and then there's sort of a special case where there is a one-form global symmetry. This one is maybe the one that's more familiar to people. It's sort of studied in, for example, this paper by Komargansky, and there are also many others on it. But so this first case, when you have no one-form global symmetry, we're saying that the line operators can end on some local operator. Well, it's not really a local operator, but some sort of gauge non-invariant operator, local operator x. And then the fractionalization classes, this omega L, is fixed by the G0 action on O of x. So for example, over here, you would say that the fact that these scalar fields are in the fundamental of this PSUN global symmetry tells you that the Wilson line, the fundamental Wilson line of the SUN gauge field will sort of transform in the, if you want, has this W2 class that's associated to the fundamental representation of PSUN. So there's a nice picture for this, which I'll maybe draw over there. Yeah, that's right. Yeah, so it's sort of like there's no one-form symmetry that participates in the symmetry fractionalization. Although there are interesting cases where this symmetry fractionalization sort of mixes with a one-form symmetry, which I can maybe comment on later. But bless you, I don't remember the examples in our paper. I didn't prepare them, unfortunately. Let's see. Yes, what's up? Oh, yeah, perfect. That's exactly what I'm about to draw. So here I have a line operator, ends on some local operator O, and I'm going to draw 5 of them. Okay, so you can first, essentially there's 2 different ways to do something. So I'm going to take my junction of symmetry operators. This is some U sub GH, U sub H, U sub G. And what I can do is I can sort of pull the symmetry operators past the local operator. I should label it this way. So that's where I start. Here's O and here's L. And I'm saying O has some projective representation R of the zero form symmetry group. So if I pull the first leg past it, then there's going to be R of G times O. And if I pull both of them past it, it'll be R of H, R of G times O. And then alternatively, what you could have done is you could have just pulled this part, this GH factor past it. And you would get R of GH times O. And now you can relate these two by sort of doing the projective action that acts on the line. So you find that this is sorry, these are just equal up to a phase. And the phase is exactly this omega G comma H associated with this representation R. Okay. So in this way, you can see that the action of the zero form symmetries on this sort of gauge non-invariant local operator sort of fixes how fixes this projective class omega. So this is what happens when you have an endable thing. But if you have a one-form symmetry, you actually have some choice of freedom. And essentially what happens is whenever you have these junctions, you are allowed to address them by an additional one-form symmetry operator. So this is some sort of U of some C of G comma H, which is some G1 action. H again, this is G, this is H. And so what this does is it actually will shift the sort of bare projective class, omega L, goes to omega L plus this C. And so in this way, that you would say that the projective classes are a torsor over this H2 of BG0, comma G1, because that's exactly what classifies these phases that you're putting in here. Okay. Cool. All right. So one sort of nice way to think about how the projective action on lines is to use something that's called what we call a disk operator. And so essentially what happens is you can take some junction like this of zero form symmetry operators. You have some G, some H, and some GH. And what you want is to pick some G's and H's such that if you lift, so G and H are in G0, but you want to pick them so that if you pick a lift, G hat and H hat, which are in the simply connected cover of G0, that they don't commute. Okay, so and omega is in the center, well, is in the pi, it sort of corresponds to an element in the pi1 of G0. So essentially what this means is that G and H commute in G0, but they don't commute in G hat. And so what that means is that sort of when you collapse this, there will be the action of this projective phase on the boundaries will actually map to a sort of disk. So if you sort of were to draw this in d dimensions, rather than just some like infinite cylinder, this would be exactly like some sort of disk. Where here there's so the disk is labeled by some element omega, which is in the sort of quotient that you need to go from G hat to G. Okay, so good. So the sort of utility of this is that once you define this disk operator, then you the junctions of essentially what you're doing is you're working in some explicit lift to G hat. So you sort of start with some G0 global symmetry, and then you sort of pick some sort of lift to G hat. And then the junctions of the G hat operators no longer act on the line operators, but rather the action is totally mapped to these sort of disk operators. So the picture is that if you have some line operator here that punctures the disk, you can sort of pull it off of the line operator that ends on the local operator in two different ways. You can either pull it off by sort of pulling the disk sort of through the line, and this will give you the projective phase omega times L. Whereas if you can alternatively pull it off of the endpoint, and then what you would get is the projective phase, or this omega, which is in the center of G hat, which is sort of which sort of encodes the projective action of G on this local operator O. So then you get this omega times O. So altogether, this correlation function would pick up a projective phase either way, and these are equivalent. So, right, so the next natural question you have is, well, this is some sort of contractible operator, so like, how could you use this to do anything? And yeah, no problem. What's up? Yeah. Yeah, you can think of them as like wrapping a sphere and then in this G times H, or this H is sort of cutting the equator of the sphere.
You're essentially taking three operators.
Yeah, so it's like if you think about rotating it, this is like the one disk. So yeah, so essentially you're mapping the entire fractionalization action to just the boundaries of this trivial looking operator. Yes, yeah, like that. Yeah, so this is just me drawing and sort of like, if you imagine it being a disk here and then sort of filling in some higher dimension, so it doesn't just look like a line segment.
It's the same operator.
Yeah, it's the same operator, yeah. So essentially the idea is like when you start with some G0 symmetry, you would sort of draw all your symmetry defects that you had that were associated to some background gauge field, and then you would have to make some sort of choice where you lift all of their group elements to G hat. Now, if you had some sort of if you had this fractionalization action, or if you had some W2 class that was turned on associated to this background field, you would be forced to put in some disk operators. And that's sort of how the projective action's encoded. So this is not like conceptually the cleanest way, but it's like computationally like the cleanest way to do this in examples. Yes. So yeah. So in this case, this. Yes. But this is also sort of, you can also do this in the case 2, and then you would just be wrapping. Yeah. But this also, you can also use this formalism in the case where the lines don't end. And in that case, you'll just be wrapping a one-form symmetry operator on the boundary of this disk operator. Okay. Right. So the nice thing about one-form symmetries is that they give you selection rules. So for example, if you want to take the example where you have some Zn one-form global symmetry, you can imagine taking a torus. So I'm going to take a D torus, and I'm going to take some line operator L, which is wrapping an imaginary direction that I'm not drawing. And if you try to compute this, and I want this to be wrapping a non-trivial cycle in the torus. So if you try to compute this expectation value, what you could do is you could actually nucleate a one-form global symmetry operator. And this is fine because it's topological. So if you had this line operator, you would just nucleate my one-form symmetry operator. And what you could do is sort of expand it all the way so that it wraps the entire torus. So that it eventually just looks like it is encircling the line operator. And then you would say that, aha, I can contract this through an action so that you get back the original correlation function times times a phase, which encodes the action of the Zn one-form symmetry. And since these are equal up to a phase, you can conclude that the expectation value of this line operator is 0. Right. I'm a torus. So this is a G to the D minus 2. This is S1. And yeah, you can just sort of think about, yeah, if you have a circle in the torus, you can sort of blow it up, and sort of when it reaches the other side, they will, they'll sort of cancel out, and then you get two things that wrap all the way around, for example. You can also do this on the sphere. But this also holds on the torus. Right. But so what's important is that you have a disk operator that kind of looks similar, where it's like you have a codimension 2 type operator, but it has some filling in part. Yes. Ah. Sorry, I need to be more consistent with my notation. Curly U. Yeah, that's right. So for example, here I'm taking, you can take a Zn gauge theory, and L is e to the I n integral of A, and then you could just say that this UG, I guess I have a K here, is e to the I K integral of B minus 2. This one I want to be taking to wrap the torus. I'm sort of just trying to draw a slice of this circle. So I want the, oh, yeah, it's just harder to draw. Yeah, essentially I want it to be wrapping some S1 that I just didn't draw. Yeah. Because if it wasn't wrapping some non-contractible cycle, then you can contract it, and this would not hold. Yeah. But essentially the point is, if you try to do the same procedure, so you can nucleate a disk as well. But then what you would end up with is not the same correlation function, because you would have essentially the interior of the disk wrapping your entire slice. And so then you cannot obtain a correlation function, or you cannot obtain a selection rule this way. Yes. No. So this is just like the normal thing for one-form symmetries. But I have better pictures for the other case. So it turns out that symmetry fractionalization actually can buy you some correlation, some selection rules. It's just that they're in twisted sectors. Okay, so I'm just going to work sort of in an example to make everything nice. So good. So if you take some G and H, which are in my one-form symmetry, which I'm now just going to write as G, and I want them to be commuting, then I'm going to pick some lifts of them to G hat, which no longer commute in G hat. Okay, so the example maybe you want to have in mind, which I had just erased, is when G is PSUN. And then you can pick G and H to be clock and shift matrices. So here I'm thinking of G hat as the matrix 1 omega omega squared, omega to the n minus 1, where here omega is e to the 2 pi I over n. And so this is the called shift. And H hat is going to be clock, which is 0s on the diagonal, 1 on the super diagonal, and then there's a 1 in this bottom left-hand corner. So these matrices are nice. Oh, this is clock. This one's shift. These are nice because they parameterize a rational torus inside of a torus algebra inside of the SUN. So essentially what happens is that, well, they exactly satisfy this relation. Yeah. But anyways, so now the selection rule I want to derive is a little bit different. Okay, so I need to have more colors than just the 2. Okay, so now I'm going to take a line operator. I'm going to wrap cycle on the torus. So here is, this is an S1 direction, and this is a TD minus 1 direction. That's going to be true for all of these. And I'm going to wrap a G, U sub G operator along the D minus 1 torus. Okay? And so what you can do is now what I want to do is I want to sort of lift this in order to talk about the fractionalization. I'm going to choose this lift of G to G hat. So now what you can do is you can nucleate an H hat surface operator, and you can sort of bring it all the way around. So what you get is that this can be related to the case where you have G, and then you have an H inverse. So I guess I should draw directions on all of these. I'm going to draw this one this way, draw this one that way. So then this is going to be this way, and that way, and that way. So this is a GHG inverse. And then when you sort of take the product of all of these together, you get, oh, that's too close. You get a U G H hat inverse G hat H hat, which is the same thing as U of omega H hat, G hat, sorry. So now what you can do is you can sort of use this disk operator to sort of pull out this omega. And so now what you get is you get the UG hat operator back, and then you get some sort of disk operator, which you can sort of pull off. This is the U of omega. And so then sort of what you can do is you can sort of pull this disk operator and sort of contract it. But since it's sort of being pierced by this line operator, this is going to be exactly equal to this times omega sub L. So essentially, something that I guess I didn't explicitly say is that if you make some choice of a lift, so here I'm working with some G, H, G, and H, and I make some lift to G hat, H hat, and omega G hat, H hat, then this is going to be equivalent to this same H hat, G hat, G hat, H hat, times this disk operator that sort of comes off of it. And so this is essentially what I've used here, is that the fact that these don't commute actually inside of this lifted group tells you that there's an omega here, and you can actually pull that off by the action of this disk operator. And then use the fact that only the disk operator acts on these lines. That was sort of the mechanism that we used or the sort of simplification we used, so that we only have to keep track of the disk operator to talk about the action on the lines. And so then what you can do is you can totally contract this, but when you sort of pull it through the line operator, you get a phase. And then you sort of get back to where you started up to a phase. So that tells you essentially you get these selection rules in twisted sectors. Yeah, you can also do this using just without any reference to the disk and just using the projective action of the junctions. It's just way more difficult to draw because it just has a lot more steps in it. But yeah. Yes, that's correct. Yeah. And essentially the fact that the projective phase is sort of fixed by these endpoint operators, there's like a nice choice of scheme you can work with so that the disk acts just exactly, this omega phase is actually just a projective representation phase. It's not just some like random H2 phase. Or like the representative is not just some random thing. Well, I mean, so I told you this is given by some cohomology class, but you have to pick some sort of Z2 representative. So you could pick something ugly and just multiply it by some phases. But like at the end, the physics will be the same. It's just that when you work on the representation, or if you have a projective representation, there's like a nice choice, which has to do with the lift of the GLV or PGLV to GLV action as matrices. Any choice is fine. It's just nicer to work. Then there's like a nice action of like a group element in the lift on everything. Yeah. You can do it on something else if you want. You can do it on S1 times the sphere. I think I think it doesn't work for any compact manifold. I mean, I think you need orientable at the very least. You might need, there might be some other homotopy classification that I just don't remember. Yeah, it's some larger lesson. For nice enough D-1 manifolds, this holds. Or sorry, for like an S1 times a D-1 compact manifold is orientable. I think this holds. There might be there's like an asterisk there that there might be some loophole that I haven't thought about. But in general, this is true it's typically true. How about that? Yeah, that's why I was saying I think there's a homotopy like obstruction. I just don't remember what it is. Well, I mean, for the tutor, I think I can draw that one. So you sort of imagine like, you sort of, you can draw like a local patch. And then what you can do is sort of stretch this one across and that one across, or like make a rectangle and then bring it all the way across. And then you get sort of 2 circles. And then you can sort of bring them around and sort of undo that. Yeah, they have opposite orientations, that's right. Yeah, it only works for invertible. Yeah, once you go to non-invertible, sort of none of this works. Mm. I don't think so. I think it's a little, also that's, I think for one-form symmetries, that's also not totally true.
But except that infinity, we kind of
Yeah.
we got to extend order boundary.
Yeah.
Wouldn't work.
But I think one way people think about, well, sorry. Another, so that's true, is that you can talk about the infinite Wilson line and, well, sorry. No, I think the oh yeah, so that, right, yeah, the large distance one is one way to think about the confinement, but I think on compact manifolds it's actually more sharp because it's either 1 or it's 0. Yeah, it's either 0 or generically non-zero, I guess. Yeah. Okay, sorry. I'm gonna keep going. I just had an interesting thought though. Okay. Good. Yeah. So essentially, what's happening is okay. Well, so I told you that there's this. Here, I'll just write it out. So essentially, if you have some u, g times the line operator, this has to be 0. If this is on some sort of non-contractible S1, maybe on S1 times md minus 1. So when this line operator is topological, you actually get an exact degeneracy in your theory. And so essentially what happens is that these line operators you can think of as generating different states in your theory, and that and the states that are given by this sort of twisted, that are in the twisted sector for this g hat are acted on by this UH operator projectively. So if you imagine creating a state by sort of, say, cutting your manifold here, just away from the operator, you would find that this correlation function is given by some sort of, you might label it by the state by the line operator L you inserted. And since G is sort of intersecting this cut, you're in some G twisted sector. And so essentially what you show is that there are 2 states that you've constructed here, and that they are orthogonal. And it turns out when L is topological, you can show that the different L's actually, for a Zn topological, for a Zn fractional phase, you can actually show that these L's actually generate a Zn, an n-fold degenerate Hilbert space in the twisted sector. Here, what I was thinking of is just a Euclidean path integral, and I'm just making a cut here. So essentially, you have a circle. You have some state in like the twisted Hilbert space on the G twisted Hilbert space on S1 times some d minus 2 manifold, which I guess in this case would be a d minus 2, or it's like a 2 disk times. Oh yeah, sorry. Yeah. Okay. Here, let me just draw it again. Oh yeah. Good. Yeah, I think on the torus it's actually a trace. So you'd want to do this in the d-1 sphere. But everything, the same computation holds. Right, so essentially, since it's like periodic, you have like two boundaries, and you're sort of, when you glue them together, it's really just, you really have a density matrix, and you sort of, when you glue it together, you're doing the trace over it. But if you have a two-sphere, you just have one boundary on one side and one boundary on the other side, and that's just a single state. And you're just taking their inner product. Yes. But anyways, what's maybe interesting about this is that this is sort of an exact degeneracy in the theory. So for example, if you had like some topological order in the infrared, which is maybe some like one-form global symmetry, like imagine you had ZN gauge theory in the infrared, you would find that there's like this exact degeneracy in the infrared. But if you had some UV completion where you broke, for example, the one-form symmetry, but you matched it by some symmetry fractionalization, you would find that actually even in the UV theory, this degeneracy would still be exact. Whereas generically, they're sort of lifted by exponentially small corrections. It's just that the sort of twisted sector in the UV theory, its degeneracy is mapping to the exact degeneracy in the infrared. I think it's not really. I mean, this is what Nadi and Sahan were calling symmetry transmutation. Yeah, but it's just symmetry fractionalization. So yeah. I mean, it's just like the degeneracy was always there, and it's just like its interpretation in terms of like how it acts on operators maybe changes. So. Yeah, so to get this degeneracy, you would want to do it on SD minus 1 times S1. Yeah. So in the little bit of time I have left, I wanted to talk about IR phases. Oh, okay. In the little bit of time I have left, yeah, so now I'm going to talk a little bit about RG flows / IR phases. All right, so I mean, I guess I should comment on one more thing. So essentially, these selection rules are cool, and there is sort of a new example you can derive with them of selection rules, which is, so if you take an SON gauge theory plus, I think it's like, for example, scalar matter in the vector representation, you can show that the expectation value of the Wilson lines with a, what is it? Put this down. Yeah, with a particular SON element vanishes. And essentially what you can use here is the fact that this theory has a charge conjugation symmetry. And so essentially you have so this is a complex scalar field in the vector representation. So essentially this has an O2 type symmetry that you can sort of play the same game with. Yeah, so this is, yes, this is in the vector. I think I want it to be in the vector representation. Yeah, I want it to be in the vector representation. I think this is SO2N, sorry. Yeah. And here, this is a twist. This is essentially -1 in the O2 global symmetry. But anyways, this is some sort of new selection rule you can actually get from doing this. Great. Okay. Good. Yeah. So the whole dream was to sort of understand the RG flow and maybe the IR phases of confining gauge theories. And so now the whole point is that since the disk operator is topological and it sort of has non-trivial correlation function with the Wilson line, that actually implies that you can track the Wilson line. Or more precisely, since symmetry fractionalization is imposed by like junctions of zero-form symmetry operators, which are topological, then you can track the Wilson line. So right, so the question is sort of what can you get from this? So I want to sort of only consider the case where my UV theory flows to some IR theory, which is gapped. Okay, let's try that again. So now essentially what we have is, since we have this selection rule, this is some sort of constraint on what the Wilson line can flow to. And what it implies is that the Wilson line in the infrared can sort of flow to two options. It can either be the sort of non-trivial Wilson line in some sort of phase with topological order. So maybe I should say LIR, which is the case when you have topological order. Or it can flow to the trivial line, of which there are sort of two distinguished types. The first one is that the Wilson line literally flows to the zero operator. And the second one is the case where it flows to the identity operator, which is sort of dressed by some decoupled quantum mechanics on its world line. Right. So maybe I can talk about the sort of two interesting cases. So in the case where you have topological order, this is the sort of symmetry transmutation case. So here what you can have essentially is this disk operator literally just flows to a one-form symmetry operator. Essentially the bulk becomes trivial. Yeah, and then it links with line operators and sort of everything is nice in sort of our familiar case. I don't have anything to say about the RG scale in particular. It's sort of, that's an example dependent thing. This is more like a deep IR statement. Yeah, so this actually in this example, you can also have the case where the symmetry fractionalization can mix with a two group. It can mix into like a two group. So essentially what can happen is that in the infrared, if you take some number of product of, sorry, this is in the UV. If you have some number of symmetry operators which fuse and then become a one-form symmetry operator, which is what happens when you have a two group, or it can happen when you have a two group. This can be matched by the case in the infrared, where you just have some sort of new zero-form symmetry operator, which again just is some sort of bigger symmetry operator, has some bigger one-form symmetry. So essentially what can happen is a two group can be totally matched by a one-form global symmetry. And there are some examples of this, for example, in 2+1 dimensional Chern-Simons theories with matter. Good. But I think the more interesting example here is this sort of decoupled quantum mechanics. Yeah, I can look my paper really quickly. I think the example. Okay, I think this happens in U1 level K Trans-Simons. Maybe when you have K complex scalar fields with charge 1. Or it might be n times k. I don't remember, but it's one of these types of theories. And I think sorry, yeah, I just don't remember at the moment. Yeah, that's right. Yeah, yeah. Yeah. Yeah, so I think what's happening for these examples is that the Posnikov class is just is W3 of the sort of zero form symmetry group. So that's like the Boxstein of the W2, and so that's why it sort of like looks like an extension, because essentially the W2 class tells you how all these fuse together, and then it generates a one-form symmetry. That's essentially what the W2 gives you. It's sort of like an improper quantization of like a group extension. That's why. Yeah, that can also happen. You can also have a two group. This is just like one example where you have this sort of like, well, this is just like an aside comment where it's like the symmetry fractionalization can also sort of mix or like has this role in the two group, which can then also just be matched by some just yes, yeah, yeah, yes, I think that's right. Yeah, 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 exactly. I mean, it doesn't act on any like local operators or anything. Yeah, exactly. So I think in this example, you can add a mass to sort of get rid of all these complex scalar fields, and then you sort of just float it, just Chern-Simons with like an enlarged symmetry. Mm-hmm.
You're not saying that you can't.
Oh no, that's the next one. Yeah, yeah. Yes, yeah. And that's sort of true in almost all the examples I wrote down, just because I was working with complex scalar fields, and you can just always give them a mass and just, yeah, and integrate them out. So, right. Yeah. So the decoupled quantum mechanics case is pretty cool. Essentially, what's happening is that this decoupled quantum mechanics has some sort of G0 anomaly, which is exactly classified by this the fractionalization class. So that's what's happening. And so what this means, the fact that the Wilson line flows to this, tells you that the expectation value of the Wilson line just flows to the partition function of this quantum mechanics, dressed by which we can normalize to the partition function of the quantum mechanics. And so this can happen, for example, by, when you think about like the Wilson line is just some sort of spin defect. You can sort of similarly write something like that down for just a zero form global symmetry, which has this world volume anomaly. They have like not in that paper. Zohar has a paper with Gabriele Cuomo, and another collaborator, and they have like one sentence where they say like, essentially, this is like a sort of degenerate case of when you have like screened Wilson lines, for example, that have some sort of like flavor symmetry charge. But yeah, so this is, but it's a more interesting example than you might think at first. So like, for example, if you, in the IR limit where you sort of think of the radius of the Wilson line being very large, this essentially just becomes an index. It becomes like the dimension of the ground state Hilbert space of this quantum mechanics. So it's, in a sense, it's some sort of like defect index that sort of doesn't classify the phase, but it sort of like tells you something about the phase that you're in. And yeah. Yeah, good. I am thinking about the Wilson line as becoming, I'm thinking about this quantum mechanics as being gapped. So in that case, you can sort of make it topological just by sort of like taking it to be large enough so that the gap becomes infinity, and then you just have some ground states. And then in that case, it's just topological effectively. Or you can add some counter terms that shifts the energy to 0, and then it's topological. Sorry, what was that? Yeah, right. So this degeneracy is sort of always has to be like the dimension of a representation that, or a multiple of a dimension of a representation that has this like projective representation, but that does not fix it uniquely. Like essentially the point is that if you think about tuning the parameters of your theory, but like you remain in this sort of space of gapped theories, this can actually jump discontinuously. Well, I mean, it jumps discontinuously, but essentially because what can happen is you can have a level crossing in the quantum mechanics. So yeah, so this was, it's almost actually like, this is very like spiritually similar to like frame BPS indices in supersymmetric quantum field theories. There you think about some sort of UV line operator, and what happens is you have these BPS particles that can sort of bind to it, and they're sort of protected by supersymmetry. In this case, we're sort of protected by the symmetry fractionalization, but these frame BPS indices sort of count the number of states roughly in the line operator Hilbert space. And these generically jump sort of across the parameter space of the theory, and in fact are even like meaningful in like a gapless theory. So like even in like super Yang-Mills, in n equals 2, 4D n equals 2 super Yang-Mills, there's a Coulomb branch of vacua. It's a nice smooth manifold, and the frame BPS indices actually jump at different locations in the Coulomb branch, even though it's sort of everywhere on the Coulomb branch except at the two distinguished points. It just looks like Yang-Mills theory, just like a free electromagnetic theory. So I think similarly, there's something interesting to say here about if maybe, for example, you could try to cook up some example where this can distinguish between like a confining or Higgs phase. So like this is actually going to be one of my future direction points, but essentially what I think this does is this counts the sort of representation of the lightest particle in a sort of that screens the Wilson line effectively. So you can imagine if you have, I'll just draw a phase diagram. So if you think about this like setup that people have been considering recently, which is a very old setup, which is, for example, SU2 gauge theory, and you have some parameter, which is some sort of complex parameter, which looks like a mass. There's a semi-recent paper by Pushen Sin and Thomas Dumitrescu, where they show that if you restrict to this real line of this parameter, you know that there's a phase transition as you go from one side to the other. And this one you think of as looking like the confining phase, and this one is sort of the Higgs phase. But there's sort of no phase transition, not necessarily a phase transition away from this real line. But what it could be is that, well, so we think this theory is sort of gapped everywhere, except for maybe at this point, because of this, there's a jump in the SPT phase. But it might be that there are different rays where, well, I don't know, it's probably just one ray, where, not this, this can jump for the expectation value of a Wilson line. I don't know where it is, but essentially I would expect there to be some sort of jump where because over here you would think that the fermions are lighter and they're the ones that dynamically screen the Wilson line, whereas over here the Higgs field condenses and that's what sort of screens the Wilson line. So you might actually be able to get some sort of information about this transition. No, it's not going to be a phase transition. It'll be like a defect transition that's sensitive to this. So it's like sensitive to UV physics, even though the IR physics is sort of identical. That's the idea. And I don't think there is a order parameter. Yeah, I think it's just there's an SPT phase that jumps. But I don't know, there might be something interesting where it's like, so something interesting about frame BPS indices is that they sort of intersect at points in the Coulomb branch, and there you know there's some sort of phase transition that happens. So it might be that there's sort of multiple lines here, and they all intersect at this 0 point that tells you a different way to tell you that there's a phase transition. Okay, so this is a nice story, but you might ask, is there some way you would actually be able to distinguish these two from like UV correlation functions? And I'm here to tell you that the answer is actually yes, assuming you can compute anything. So let's take our theory on S1 times SD minus 1, for example. And so essentially, or what we think is that there's sort of 3 different IR possibilities. So there's the case where the operator flows to the 0 operator. There's the case where you get the identity times this sort of decoupled quantum mechanics. And then there's the case where you get some sort of non-trivial infrared line operator. And in particular here, I mean that's one that's protected by some sort of one-form global symmetry. So I'm going to look at the expectation value of the UV Wilson line. So I'm going to look at the expectation value of the Wilson line in 2 different ways. So I want to look at it wrapping the sort of non-contractible S1, and there's also wrapping some contractible curved gamma. So we know for the 0 operator, this is always going to be 0 for both of these. And we know for the case where the infrared line operator is protected by one-form symmetry, it'll vanish on a non-contractible cycle, and it'll be 1 on a contractible cycle. But if a line operator flows to decoupled quantum mechanics, it's sort of going to be independent. It'll always be equal to this the quantum mechanics. So in this way, you can sort of distinguish between these 3 phases. And in fact, there's actually another way you can do it. So you can also, there's another way you can do it that sort of does not rely on this assumption that the line operator is protected by a one-form symmetry. It just requires that it's topological. What you can do is you can again look at an expectation value in a twisted sector. So here I'm looking at this wrapping the SD minus 1. Yeah, SD minus 1. And then you can take the Wilson line wrapping the S1, and you can take its complex conjugate also wrapping the S1 at some other value. So if these floated topological line operators in the infrared, then this will just flow to the expectation value of the line operator, of the symmetry operator wrapping the SD minus 1, which will be non-zero if there's no 0-form spontaneous symmetry breaking, which for G continuous we sort of would want because otherwise it's gapless. In the other case, where you have the quantum mechanics, this will actually be 0. And the reason is that this expectation value will actually factor into, will sort of be the expectation value of this operator times the expectation value of this operator, which each vanish locally. And essentially the reason is that you're summing over, essentially you're summing over this clock operator in a projective representation, which has trace 0. So this is another way you could, you can sort of distinguish between this like infrared topological phase and this decoupled quantum mechanics. Yeah. So this is pretty much the end of what I had prepared. I guess one last comment is that we think that there's a difference, that there's a phase transition between these two phases. I mean, clearly there's going to be, well, yeah, there's definitely a difference between the operator flowing to a non-trivial topological operator and the 0 operator. But we also think that there's going to be one where it flows to the a decoupled quantum mechanics. Yeah. Yes, I think so.
Even though the Wilson line alone acquires.
Yes. Wait, well, it's also in this twisted sector. So it's. Well, okay, so also in the confining phase, when you don't have a one-form symmetry, there is no area law.
But still you can set the experiment based on two-polar evolution.
Yeah, that's right. Yeah.
Then you would say that
Yes. Yeah, exactly. It's very similar to this. I think, yeah. Because you would say essentially this is really a diagnosis of the screening of the line. Yeah. I mean, yeah. Essentially, this also tells you nothing about just the normal like Polyakov 2-point function. This doesn't tell you anything about that. But what it tells you is that in the twisted sector, it's either exactly 0 or it's exactly non-0, and that is a sharp distinction. So I don't want to call this an order parameter, but it's interesting.
about this analogy. Do you have any example where this dimensions index is different than the smallest possible projective representation of the group in an open neighborhood? I understand that.
Yeah.
Maybe jump at some like 0 loci space, but like.
Yeah, right here.
Is there any cases in which it's different than the small entire open region of parameter space? Right, I guess that's what you're alleging here in this case.
Yeah, like so. For example, if you just took like SU2H theory with two scalar fields in the spin 3/2 representation, I would have guessed that. Oh, I guess that's in this. Yeah, I'm not sure what it would be essentially. I've never computed this. I don't know how to compute it. You probably need a computer. And you probably can only do it like computational, like yeah, computationally.
No.
The non-supersymmetric setting.
For this defect setting. Like in the SUSY setting, they answered my questions, yes. But in this case, I would sort of think that like in the same way that if you look at a quantum mechanics theory, generically the ground state is or if there's an anomaly which is the ground state, its dimension is the smallest projective representation. I don't think there's
Generically?
yeah, generic.
Not just in like the nice examples we like to consider. I mean, you can definitely can.
You can't really have symmetry breaking quantum mechanics, right?
Y-
In zero plus one.
yeah, yeah, yeah. Yeah. Yeah, no, I haven't studied this. I just think it's an interesting, I mean, essentially like, I know this is some sort of index and there's no reason why it can't jump. But I have no examples. I think it's interesting.
I guess I'm wondering whether it jumps or whether it's sort of like it enhances the special loci and generates as small as possible. You can't.
Yeah, it could just be.
You need the first thing. It's
Yeah, that's right. Yeah. I think I was just thinking of it, I was definitely thinking of it in analogy to this. And like what might happen if you, for example, were to take a soft SUSY breaking deformation or something. Maybe this would flow to this, for example. I'm not actually sure. I have no ideas. I think it's an interesting open problem. Yeah, good. So essentially what happens is the right. So the way that the quantum mechanics partition function vanishes in the twisted case. So it's like UG times T quantum mechanics, whatever. This ends up being like locally a trace over the quantum mechanics Hilbert space of like the group operator. And essentially the way we've constructed it is so that this trace vanishes. And so if these two Wilson lines both decouple, then this correlation function is just going to be the trace of this RG squared, where the square is on the outside, just because it's totally local. Yeah, that's right. Just because it's like the, yeah, that's right. Yeah, that's correct. Yeah, I'm thinking of it like this picture where you have an SD minus 1 and S1 here. And here's my like UG. And then I have two different line operators here and here. Yeah. And just the fact that they're not topological in the UV sort of tells you that this could be non-zero. But if they're topological in the IR, then it has to, these sort of will cancel against each other. But if it's just a decoupled quantum mechanics, then it'll vanish locally because just there's a trace for each intersection point.